tree diagrams. In this lesson, we're only going to focus on tree diagrams, how to build them, how to use them, how to solve problems with them. Ivy loves them, I love them, so we're going to learn how to use these. Let's start by looking at this example here. Consider two archers firing simultaneously at a target. These are independent events. Lee has a probability of 3/4 hitting a target, and Yuka has a probability of 4/5. So what you do is you just go, okay, Lee has a probability of 3/4, you start with Lee. Always like to draw a little character. Right, and then hit is 3/4, miss is 1/4. Then you go Yuka, and Yuka's the next part. So again, they don't affect each other, so you just go, Yuka has a 4/5 chance of getting hit and a 1/5 chance of getting a miss. 4/5 chance hit, 1/5 chance of getting a miss. Right, and if you see this, if I want to figure out what's the odds that they're both going to get hit, all you do is you multiply that line. So hit for Lee and a hit for Yuka. So you just multiply that, 12 out of 20. What's the odds Lee gets a hit and Yuka doesn't? Hit, miss, and you just get that probability. Lee misses, Yuka doesn't, miss, hit, and if most probably they both miss, you just go miss, miss. That's kind of the way it works. So let's make our own right here. So the best way to do this by example. So in this problem, Carl's not having much luck today. His car only starts 80% of the time, and his motorbike starts 60% of the time. So first I want to draw a T-diagram. So let's start like this. Let's say this is the car. It doesn't matter which one you start with first. Right? I like to draw us so you know, because a lot of people tend to put something here. I just want you to know, no, that's us deciding. So his car could either start or not start. So you can put whatever you want here, like not start or just start with a prime. A lot of people do that. So that means not this thing. Starts 80% of the time. That's my 80. So must not start, right? The complement of that, 1 minus 80, 20% of the time. Then from here you can branch out. Now remember that independent events, they don't affect each other. So that means that from here we can write the motorbike one. So we're going to go, from here we're going to write, this is our motorbike. Right, same idea, it either starts or it doesn't start. Now motorbike has a 60% chance of starting. That means not starting will be 40%, 1 minus 6. Do the exact same thing down here. Right, not starting will be 1 minus 0.6, the complement of 0.6, so 0.4. Now let's look what they want us to solve. So use a tree diagram to find, let's do the first one. Both will start. So all I do here is just follow the two starts. So it'll be this line and this line, right? Car starts and motorbike starts. So if you want that, you just multiply the line, 0.8 times 0.6, or 0.48. Those are the odds that both cars will start. Now, if you want the odds that only Carl's car will start, Carl can only use his car, so only his car starts. So you're going to go, okay, his car's going to start, so this line here. And that means that his motorbike doesn't start, so you have to use this line down here. So for 2, it's going to be 0.8 times 0.4, or 0.32. That's how you do a basic one. Now let's get a little more advanced. Now, the problem's going to be a little confusing, but tree diagrams help it a lot. 2 boxes each containing 6 petunia plants that are not yet flowering. So box A contains 2 plants that will have purple flowers, 4 plants that will have white flowers. So this is right. So box A, right, has 2 purple and 4 white. Box B is in 5 plants. We'll have box B contains 5 plants will be purple, so 5 purple and 1 white. A box is selected by tossing a coin, and 1 plant is removed from random from a determined probability that will have purple flowers. So we're just looking for the odds that's going to be purple. So we start off, right, we're going to pick a box first. So here's us. Right, and we can pick a box. You can pick box A, or you can pick box B. That's my perfect tree diagram. Now the way they choose which box you go to is right here. It says you toss a coin. So that means it's 50-50 shot. So this is like 1 out of 2 and a 1 out of 2 shot. Right, so that's the start of my tree diagram. I know it looks terrible, but bear with me. And now from A, right, you branch out. If you haven't selected box A, you have 2 choices. You can have a purple flower or a white flower. Now notice in box A, there's 6 flowers total, so the odds of getting a purple flower will be 2 out of 6. Odds of getting a white flower will be 4 out of 6. If you happen to get box B down here, same idea. Different odds though. Right? Box B, purple is 5 out of 6. There's 5 purple, but 6 total. And the odds of getting white is only 1 out of 6. Now remember what we're looking for is odds you can get a purple flower. So this is slightly different than last time. It's a little more complicated. There's 2 ways to get a purple. You could select box A and get a purple. Or you could select box B and get a purple. When this happens, it's actually a very easy mathematical concept. All you do is you multiply these together, like we did before. So A in purple would be 1/2 times 2 6. And then you add it to the other line. So once you have to add another line to it, you just add it. So it could be B in purple. So it'll be 1/2 times 5 6. Do a little math. So 2 out of 12 plus 5 out of 12. And you have a 7 out of 12 shot of selecting a purple flower from this situation. Let's do one more example before we move on to a slightly different type of tree diagram. So let's look at this one. The probability it will rain tomorrow is estimated to be 1/5. If it does rain, Mudlark will start favorite in the horse race with the probability of 1/2. With probability of 1/2 of winning. Isn't that cute? Mudlark, because he likes to run in the rain. Anyway, if it is fine, he only has a 1 out of 20 chance of winning. Yeah, he loves the rain. Display the sample space of possible results for the horse on a tree diagram, hence determine the probability that Mudlark will win tomorrow. So this is a perfect example of how you use a tree diagram. It makes things so much easier, right? So if I could draw a horse, I would, but instead I'm going to draw us, the jockey, or the bettor. Hey, there's my money, right? And then if it rains, so you have two. First, let's go with the rain or not. So it's gonna rain or not, right? So rain, and then no rain. So I'll just put rain, prime. You can also put fine or whatever you want to put, right? The odds of it rain tomorrow is 1/5. Now remember, when you do one of these, it has to equal 1, like everything probability, right? So if the odds of rain tomorrow is 1/5, the opposite of that, the complement of that, I should say not opposite, complement, is going to be 1 minus that, or 4/5. Right? This line here should always equal 1. Then we move on. So if it does rain tomorrow, it says that Mudlark has a 50% chance of winning. So if it does rain, his chance of winning is 1/2, which also means his chance of losing, right? Again, this should equal 1 here. It's also 1/2. That's my L. If it does not rain, if it's fine tomorrow, when he has a 1 in 20 chance of winning, and if he has a 1 in 20 chance of winning, that means he has a 19 out of 20 chance of losing. Because again, these should always equal 1. Right, so that's our little tree diagram. And then the question is, what's the odds of Mudlark winning tomorrow? I'm telling you right now, you better hope for rain. Right, the odds he's going to win tomorrow, we just look at, oh, there's 2 ways to win. Just like we just did, all you have to do is, okay, let's get to that way of winning. So you multiply this by this, so it could rain and win. So 1/5 times 1/2. But you can also do it this way. When there's more than 1, you do the same thing, find that line, and just add it. So it could not rain and he could win. Fat chance, but still could happen. 4/5 and 1/20. Multiply these together, I get 1 out of 10 plus 4 out of 100. And I guess we could do some common denominator, multiply this by 10/10. So 10/100 plus 4/100. He has a 14 out of 100 chance of winning, or 14% chance of winning the race tomorrow. Take those bets. Up until now, we've been doing mostly independent events. Let's move on to dependent events. So also known as snapping without replacement. So when we do dependent events, the effects of what happens on the first turn totally affects what happens on the second turn. So right, that's the thing we talked about a little bit earlier with the with replacement and without replacement. With replacement makes it independent. So like you draw marbles from a bag and you put those marbles back in. So the odds are always going to be the same. Right? So independent events, it doesn't matter. It's always the same odds. Or it doesn't change the odds of the previous term. Now the one that's way more interesting is with replacement, right? You take that marble out and now it's gone from the list. That's me highlighting it again. Right? So that changes the odds the next time around. So as you can see here, getting a red, a blue, or or yellow, it's 2 out of 6. But now once you did that, you already picked the blue. So if you look now, there's only 5 things left, and you already picked one, so there's only 1/5 blue left. If you look at this first row here, 3, 6 getting red. Getting red again, well now there's 1 less. It's only 2 and it's out of 5. Right? But back here with replacement, where you put the marble back, nothing changes. Getting blue is 2 out of 6. Getting blue is still 2 out of 6. Right? Getting a red is 3 out of 6. Well, you put the marble back, so now getting red is still 3 out of 6. Right? With replacement, a lot more interesting. Numbers start to change. And what you did on the first turn affects what you're going to do in the second turn. Let's look at a quick example. I'm not going to go all the way because it would be madness, but just to get the idea of it. Look at this first one. A box contains 3 red, 2 blue, 1 yellow marble. Probability of getting 2 different colors. So again, it's gonna be, if I wrote them all out, it'd be kind of large. So like here's us, right? Here's sorry. Here's red. You could get red, or you could get blue, or you could get yellow. Now I'm only going to find red here because you have to. They want you to draw 2 different colors in the nice King's English way of spelling colors. Right, so I can draw marbles again. So red, blue, yellow. I have to do this for all of them. I'm gonna spare you the time. But the idea here is, when I do that, let's look at the odds. Right, getting a red is 3 out of 6, and then getting a blue would be 2 out of 6, and getting a yellow would be 1 out of 6. When we go again, well, you put the marble back with replacement. That means everything's back to normal. It's Groundhog's Day. So it's 3 out of 6, 2 out of 6, and 1 out of 6. And you do this for all of them. After that, though, I'm not gonna do this for all of them, but they want find 2 different colors. So if I was doing this line, this would be red. I can't pick red again. I go red, blue. Right, red, blue. Plus, that happens a lot more times. I have to go with red. I can do red and yellow. Those are different colors. Right in the middle here, you can do blue, and it'll be like blue and red and blue and yellow. So there's gonna be a lot more of these. You can add them all up. Or if you know the complement, you can just do red, red, blue, blue, yellow, yellow, and then subtract that from 1. That would also work. Anyway, I want to show the difference between that and with replacement. If replacement does not occur, I mean without replacement. Without replacement is what it's generally written as. So that one, just to get the idea, here's us. Red, blue, yellow. It's like before. I'm going to spare you some time. I'm not going to do all of them, but just to get the idea across. Right over here, red would be again 3 out of 6, 2 out of 6, and 1 out of 6. But now, when you get to this line here, the assumption is you picked the red the first time. You went red the first time, so there's 1 less red. 2 out of 5, right? 1 less red, 1 less marble in total. You still didn't pick any blues, so all the blues are still there. 4 blues. And you didn't pick any yellow, so there's still yellow there. Right? That's how you draw that second tier line there. I don't have space for B, but I'll do the same thing for Y, right? If you do this for Y, you go red, blue, yellow. The assumption is that you picked yellow the first time. So you still have all your reds left. 3, and there's only 5 total now. Same thing with blue, right? You picked yellow first time, so you still have all your blue. And you picked yellow the third, and then for yellow, you assumed you picked yellow, so there's actually no more left. And if I want different colors, same idea. I can do red, blue, yellow, blue, yellow, yellow, red, yellow, blue, and add them all up. Hopefully that gives you some idea of the importance of with replacement and without replacement. Let's look at another long one. I don't want to bother you having me writing, but in this one, the back contains 5 red, 3 blue marbles. 2 marbles are drawn simultaneously. So again, remember we talked about this before. Simultaneously, when they say that, you're taking at the same time, so it can't be replaced. Simultaneously is automatically without replacement. If you're taking at the same time, you can't change it when you're taking it at the same time. So just keep that in mind, right? Simultaneously is without replacement. So look at the problem they did here, right? So red and blue. So they went, here's us. Can't forget that. Right? You could either go red or you could go blue. There's 5 red, 3 blue, so total is 5 out of 8, 3 out of 8. And then you're doing simultaneously, so you can draw again. Well, remember, on this line, the assumption is you drew red the first time, so there's 1 less red, and it's out of 7 now, because you picked the marble the first time. You haven't picked any blue, so it's 3 out of 7. Down here, you assume you picked up blue the first time, so now there's one less blue, 2 out of 7, and all your reds are still there. And then another big part about this is, look, notice the wording. At least one red. So one or more red, right? At least one means x is greater than or equal to 1. So in this case, when you draw 2 marbles, you can have 1 marble or 2. You can have 1 red or 2 red. If you look right here, right? So you could get red, red. That's 1 red. So you could do this line and that line. That's 1 red. But you can also just do red, blue, because that's at least 1 red. And you can do blue, red. Basically, anywhere you see a red, you want to do that one. And that's what they did here. Multiply those together, multiply those together, multiply those together, add them all up, and you got 25 out of 28. Or if you prefer the little shortcut method, well, they're picking everything but blue, blue, so do 1 minus blue, blue. So that's what I did here. They got the answer. Before we finish this video, let's go over the last couple examples. So look at this one. A board game uses the spinner shown. If the first spin is red, then the spinner is spun a second time. So if you spin it and you get blue, you're done. But if you spin it, you get red, and once you spin it again. So first thing I'm gonna do is let's complete this diagram. Well, look at this thing here, right? That is 1/4 blue. It's on a quarter circle. So the red must be 3/4. So on a spin, you have 1/4 blue. Red is 3/4. Now when you spin it again, it's the exact same picture, so nothing changes. They're independent events. Blue is still going to be 1/4, red is still going to be 3/4. Now look at the question. Calculate probability that the end result is blue. So you just want to get blue any way you can get it. So there's a blue right there, there's a blue right there. The way you get this blue, you just spin it. 1/4. The way you get this blue, it's red and then blue. So, right, anytime it's a straight line, not a straight line, anytime it's a line, you multiply it. 3/4 and 1/4. Right, anytime you have multiple lines, you add them together. So you just get 1/4 to 4 plus 3/16. If you want to add them up, you do common denominator, multiply this by 4/4. And you get 4/16 plus 3/16. Also known as 7/16. That's the idea. Let's do one last example. Get out of here. The bag contains 7 yellow and N blue markers. So all we know is you got 7 yellow and we have N blue. 2 markers selected at random without replacement. The probability that both markers are yellow is 3/16. Find how many blue markers are in the bag. Right, so it's a little more theoretical, but it's the same idea. Here's us. Right, we're drawing markers from a bag, and you can either go yellow or blue. Now yellow is 7. Over, now here's the hard thing, right? We gotta think of the total. Now if I said you had 2 blue and 3 red, you'd be like, oh, the total is easy, that's 5. How do you find that? You add them up. So my total here, I have 7 yellow and N blue. You just add them up, N plus 7. That's my total. So when I select the red, when I select the yellow, it's 7 over N plus 7. Right, my odds of selecting a blue marker, well, they're N blue, so N over N plus 7. Once you do that, you select another marker, so you can either get another yellow or another blue. Now notice it says without replacement, so they don't put it back. So odds of getting yellow, well, you picked yellow the first time, so there's only 6 now. Right? And then you take 1 off of here. It's not as bad as it looks. N plus 7 minus 1. N plus 6. Right? Odds of getting blue. Well, N, you didn't pick blue the first time, so it's still N. Now over N plus 6. Down here, assumption is you did pick blue the first time, so there's 1 less blue. How do you write that? N minus 1. Over the bottom, N plus 6. Right, we lost 1 on the bottom too. And then yellow, we didn't pick a yellow the first time, so it's still 7 over N plus 6. And then to finish this out, what's probably that both markers are yellow is 3/13. So both yellow. I want yellow, yellow. Only way I could get it is right there. So it's to be 7/n+7 times 6/n+6 equals 3/13. Right? If I want to simplify that a little bit more, it would be 42 over n squared plus 13n plus 42 equals 3/13. Probably do a little cross multiplication and get something equals, and then right set equal to 0. So get something equals something, set equal to 0, and solve. It looks like it's going to be kind of ugly. I would also use a calculator, y1, y2. But that's a video for another day. And we are done here.